I see here. May I start already?
Yes, please.
Okay, so thank you very much for the organizers. It's a pleasure to be here with all of you, especially because I spent a very nice time both scientifically and personally in Clermont-Ferrand. So it was a very time period spent there where I learned many things, and so it's very nice to be here. It's unfortunate that we are doing this virtually, but I think everybody understands the reason why it is so. So I'm going to talk about some works that I'm currently developing. It's probably a little bit general, more broader probably than the physics of polaritons itself, because it's about nonlinear structures that you can generate in superfluids. And the idea is to do some sort of statistical physics on top of what we call, or I'm trying to call, the dark soliton gases and vortex gases. Some of this work has been developed already, a part started already in Clermont-Ferrand, so I think it's interesting to bring it here with a different perspective. So the idea is, so I will talk a little bit about the motivation, why we are doing this kind of physics, and why we are interested in bringing solitons and vortices to the phase space. And the idea is that, as it will become clear, is that we need this with the hope of describing low-dimensional turbulence, because low-dimensional turbulence, as you know, in most of these systems occur because of interactions between sound waves and these topological structures that appear, either solitons in one-dimensional systems or vortices in two-dimensional systems. So it is desirable to understand what is the physics behind all these turbulence mechanisms. Of course, you can do numerics and you can extract your cascades from that, but it's always interesting in trying to understand microscopically what is happening and what is the different contributions and their levels of contributions to the final cascades that you see in your numerical simulation. So that's pretty much the whole spirit that you have under these things. So why bothering about soliton, vortex, and soliton and vortex gases? The idea is that, as I was explaining, that they participate and they are primordial in the description of low-dimensional turbulence. Okay, so if you go to higher dimensions, three-dimensional fluids, for example, what you have to deal with when you are talking about strong turbulence in quantum fluids is these vortex tangles, right? In low-dimensional things, you don't have tangles because they are dimensions imposes lots of restrictions, and these restrictions are very crucial to the dynamics of vortex and solitons themselves, but not only individually but also collective. And that's exactly this collective nature of the interaction of these things that we are interested in. And then with a kinetic description, we'll be able probably to describe out of equilibrium features that remain unexplored, right? So probably all of you are aware of this Onzaga theory for vortex gases that appear in two-dimensional systems that was developed by Onzaga himself to describe point-like vortices in superfluids. But these theories, it was an attempt to make statistical physics out of vortex gases, but they are for equilibrium systems. So if you displace a gas out of equilibrium, what happens to this system? Which is exactly the situation in a turbulent situation, in a turbulent scenario. And then you eventually can apply this to the application of impurities, but pretty much inspired by the early experiments in liquid helium, where you have impurities pinning to vortices, but this is something that you could probably do after our framework is developed. So just to make a brief summary, you all know what dark solitons are about. Just to put everything here, who are less familiar with these structures in the same grounds, we'll be talking for a while about these quantities here. So they are represented by these as a nonlinear solution to the Gross-Pitevsky equation. And here we are neglecting polarization, spin degrees of freedom or spin degrees of freedom for a while. And the idea is for you to understand that these objects are objects where the cinematics, so the velocity, which is the parameter that appears here in this wave function, is a parameter that affects pretty much not only the shape, so let's say the density of the wave function, but also the phase. So this has important implications in what is going to be the final results or let's say the particle behavior of this object. If you look at this soliton as a localized object, because you can look at this as a localized object, because the finite size of this object is typically the Healy length of your system, this C that appears in the equation. So you can look at it, if you are interested in dynamics much larger than this C, than this Healy length, you can look at the soliton as a point-like particle. And that's pretty much the spirit that we want to capture here. So then we go to a two-soliton solution, and this is something that is very well known since the 70s or even before that, by the inverse scattering transform theory, that you can find a solution of in this family of nonlinear Schrödinger equations where they contain two solitons. And these two soliton solutions are very interesting, is that when if these two solitons cross each other, as we know already for a very long time, there's a phase shift of pi in the wave function. So this is a clear manifestation that solitons or soliton, a gas of solitons is a Fermi gas in the first beginning. And this is actually, as you probably know as well, very aligned with the Lieb-Linear theory, where it states that soliton excitations in a one-dimensional Bose gases are of Fermi nature, right? So this is a result that it was established in the type 2 excitation. So they are called the type 2 excitations for Lieb-Linear gas, and they have recently been demonstrated that they indeed correspond to these dark solitons that we know in Gross-Pitayevsky equations. So this is just a sketch for what happens to the solitons. If the relative velocity of the solitons is lower than half of the sound speed, local sound speed, the solitons just repel each other and they bounce. So this is the first thing, no crossing. And if the relative velocity of these solitons is larger than half of this local sound speed, they cross each other. So what we are interested here is trying to understand what kind of potential, if you look at these as particles, what kind of potential describes this kind of features, right? So to do that, what we do is as a variational analysis of this problem. So we defined a pair wave function that is the product of these two solitons, separated by a distance y, and this distance y will be a parameter that we are going to try to describe variationally. So we are going to find some equations of motions for this y variable, which is the mean separation between the two solids, okay? So we started already doing something along these lines in our papers of 2013 and 2014, where we described, we put for some statistics for this, we make use of this kind of ansatz to describe some interesting features of solitons, like high-speed DC magneticity and crystallization, and kind of interesting aspects on top of soliton gases. So the physics comes like this. You can say that this, you can describe the acceleration as a derivative of some sort of energy, and this energy is just the average energy over these pairs, right? So here's the variation, the ensemble energy of this Gross-Pitayevsky Hamiltonian that you can sandwich with this your variational ansatz that you use. And from this results two terms. One is the kinetic term, and the other one is the interaction term. What is interesting here is that both of these terms now are dependent not only on, so you cannot do a separation in velocity and position terms, but they are effective potentials. And in the sense that they depend on the parameters of this wave function, and because it depends on both parameters of this wave function, so the velocity and the position, they are they can be called effective potentials. So if you can do the maths, there are lots of very cumbersome expressions for both of these terms, but in the very low concentration, so high separation of solitons, you can say that kinetic energy of the two solitons is twice the energy of each twice the kinetic energy of each soliton separated, and is given by this quantity here. By the way, this beta is the relative velocity as is defined in this slide here. So is velocity of the soliton divided by the sound speed. Is the usual definition in relativistic physics. So this is the dispersion of singular dispersion for the kinetic energy for two solitons that you have to take out at the end in your dynamics. The same for asymptotic behavior for the interaction part. So it's something like that. Is mu is the chemical potential, and this exponential decay. And here you have the full, for comparisons, you have here the full expressions in solid lines compared to the asymptotic behavior of this interaction energy. And you can see that this potential is a soft core potential, right? So the effective potential that solitons feel is a soft core potential. And this will be very interesting in what follows. So what is the spirit of our formulation? What we go now to do is, okay, we have we know exactly what happens to one soliton, we know exactly, or more or less, what happens to two solitons, and we want to describe an ensemble of N solitons, a gas of solitons. So the way we do this is via this Klimontovich equation, where we can go describe this in terms of this microscopic density in the phase space. So you can define what we call, so this Klimontovich equation will depend on this potential that is the microscopic potential. So the potential felt by a single soliton due to all the solitons existing in the system. But this description is very demanding computationally. So what we say here is that we are interested in a smoothened distribution function where this NV, where is the true, let's say, microscopic with all these micromotions of solitons in the phase space, is a smoothened function plus a fluctuation. And in this case, what we recover is equivalent of what we call in plasma physics a Vlasov equation. And this Vlasov equation is formally equivalent to a Boltzmann equation without collisions. But the term of the interaction, so the third term that you see here in the equation, derivative of x of this integral, is a potential that is smeared out over all these distributions. What is the crucial point here is that we are saying now that each of these solitons, because of the short range nature of this interaction, will see each other via these pair wave interactions, right? So we have pair soliton interactions, and we'll smear out over the whole distribution. So this is, of course, an approximation, but we are going to be interested to see how accurate this approximation is a posteriori. So this is the potential that in principle is a function of not only the position, but also the velocity as I explained before. So if you work out the mathematics a little bit, you can recover what we call this kinetic dispersion relation. And how you do that, you assume that you have initially prepared your gas in a certain configuration, let's say some equilibrium distribution, F0 of velocity, plus some fluctuations. And you linearize this initially non-linear equation, which is this kinetic equation that you have here. If you linearize, you can get some sort of kinetic or Landau dispersion relation, right? And this dispersion relation here depends on the very shape of this Fourier transform of this potential interaction of the solids, right? So now you have a distribution that you can have either a cold gas or a thermal gas of solitons, or whatever distribution you do. You can also have two beams, two gas of solitons colliding against each other. So you choose your situation, but you have to convolve these with the interactions, right? So this is the term that is in between these pairs. And in the left side, you see the plot of this Poisson potential in Fourier transform for different values of this velocity. So we work out this for a situation. This is something that I'm doing with a master student, Maria Clara. And we started with the obvious situation. Okay, so if solitons are indeed fermions, they should be described as a Fermi distribution. And this Fermi distribution here is something that goes up to this Fermi velocity, the one-dimensional Fermi velocity. So you fill these solitons up to this Fermi velocity. This Fermi velocity, by the way, is just a function of the density of the soliton gas itself. So the density of the soliton gas itself is this capital N naught, right? So it's the number of solitons that you have per unit length, if you want. So if you work out this, and you have a little patience in simplifying your expressions, you get that the dispersion relation, you get a sound wave, a sound mode for this soliton gas. And the sound mode of the soliton gas is what we call here soliton first sound. Is very similar to the Bogoliubov sound speeds in terms of let's say, microscopic dependence on the parameters, but you have an additional term here, which is this N0 times C. So N0 times C is the concentration parameter, right? So it says how many solitons you have per unit length. So it's pretty much the sound speed, if you see, times this parameter that conveys the concentration, that describes the concentration of the soliton gas. And this is pretty much the dispersion relation of this sound that you get. So our guess is now to go to numerical simulations, starting from the really very beginning, where you have a soliton gas, and try to see whether or not these sound modes exist. As you can see already from this picture, there's a sound wave that is produced in this configuration, right? So we excited this we made this gas of solitons here that you can see, and we made small perturbation and let it evolve in time. As you can see, these red lines here reproduce exactly a wave, a sound wave that appears on top of this soliton gas. And this is exactly the sound wave that we are going to do a spectral analysis on. So we see this. This is in Fourier space. Then you Fourier space the whole thing, and you see exactly this. So there's a very faint line here that you probably can see in your screen, and this very faint line is what we identify as the Bogoliubov mode, because we are solving Gross-Pitaevsky equation from the beginning. Okay, so the Bogoliubov mode should be there, and you see very clearly here that a mode that we can relate to our kinetic mode, or our zero first sound on soliton gas. This is red line here. So the theory and the numerical experiment. And you see here this vertical line that I'm putting here in the plot is what is the validity of this. So our model is expected to be valid up to this vertical line. So in the very long wavelength regime, because of course, if you resolve the solitons internally, you are out of the concentration, right? You are out of the range of the applicability of our theory. But it seems to be more or less reasonable against in comparison to the theory. So it means that for sure this mode exists, right? And this mode is related to some sort of interaction between the solitons. It seems to be captured very well by our smeared out pairwise potential, but it deviates for higher values of the wave vector. It deviates a little bit. Of course, we suspect that many other aspects here are present, and we are not included here. When one of them is something that we are trying to include in the next steps of our work, is interactions with phonons, right? Because solitons will interact with phonons as well, and there's a term that will be the soliton-soliton interaction mediated by phonons and not by the mean field itself. And then there's this mode here, and this mode here that we are trying to understand may be probably related with the fact that we are not doing the right guess about the initial conditions, right? Remember that I said that the gas the initial distribution was a Fermi distribution, and our Fermi distributions provides in the dispersion relation a single mode, which is this red line here. But in the Lieb-Lininger theory, you know that there are two modes. And these two modes are related to the fact that one is fermionic and the other one is bosonic. So we have to work out, we are trying to understand now at this moment, whether or not this second mode that appears here that we see in the simulations is related or not to this Lieb-Lininger first mode that is described in the literature. Another effect that you can add is really this Casimir-like effect. We call it Casimir, but it's probably a little sloppy. From my side, from my point of view, I'm not really afraid of using these analogies because it's pretty much what is happening. So if you have sound waves outside the solitons and sound waves inside the solitons, there's a difference of pressure, and you can use the same sort of reasoning that Casimir himself used for these plates and calculate some sort of interactions. And this interaction is long range in nature. So you can correct the beam, you can go to beyond mean field and calculate this polarization with, including these effects. And what you see that for the same parameters is it slightly goes lower, so it increases a little bit the validity of our regime. So it suggests at this stage, so this is not a work that we have finished already, it suggests that probably this effect has to be taken into account in more systematic calculations, at least for this mode.
2 minutes. 2 minutes.
Sorry?
You have 2 minutes.
Okay, I will conclude.
2.5.
Okay, this is pretty much what I have to say. I will not have time to say what happens to vortice. But if you go to the vortice case, just for you to have an idea, and this is something work that we are developing currently right now, is that in the vortex cases the situation is more complicated, and the problem in vortex is that the interaction energy is logarithmic with the distance, right? And this is a consequence of the velocity profile of the fluid around each one of these vortices, right? So if you apply Onsacker-Feynman quantization conditions to each vortex, you have these profile velocities. And it results in interaction energy between two vortices like this. So if you repeat the procedure that I was trying to tell you before, so I will just show you the final equation. You get some sort of equation that is something like that, this red equation here. And this red equation is exactly a Vlasov equation, but now this acceleration term is something that depends on the logarithm. So you see that you have to do smear out of this logarithm here. So it's this, you have to deal with divergences here, these infrared divergence that you have in this vortex gases. So, and as you know, moreover, this is very important to have finite size effects in the description of vortex gases. So what we are trying to do at this point is just to see whether or not this provides one kind of mode on top of this vortex gas. If you do the math, what we see exactly is that because of the long range nature of these vortex gases, we predict what we call a plasma frequency or a plasma mode on top of this. So on contrary to the soliton gas, because the soliton gas has short range interaction, so you have a sound wave. Here you have a plasma wave. So this is described by some sort of cutoff. So H0 now is the two-dimensional density, okay, of vortexes, and you see that it has some sort of. So now what we are going to try to see in our numerical simulations is whether or not you can excite this mode. And the reason why we suspect people have not seen this mode in vortex simulations is that because these modes cost some energy, right? You have to excite this mode to see this vibration on the soliton gas, because this is a gapped mode. So if this is a gapped mode, if you prepare your vortex in very low energy, don't provide any perturbation, you'll see the motion of the vortices, but you don't see this collective motion of the vortex gas. So this wave that propagates on top of the vortex gas. So probably this is one of the reasons. The other reason is just because nobody looked at it in very detail. So thank you very much for this. This is the stage of where we work are. We are now developing some numerical simulations to try to see these modes. But this is pretty much what I have to say about these kinetic equations or solitons and vortex gases. Thank you very much.
Thanks a lot. We have time for several questions. I can maybe start. The particularity of polaritons is that the nonlinearity is provided by the excitonic part. So yes. If we work in the polariton basis, then the interaction strongly depends on the excitonic Hopfield coefficient that is k-dependent, and this would introduce, for example, non-locality in Gross-Pitayevsky equation. Yes, or we can work in the exciton photon basis, and then there are these works of Nina Voronova and Lazavik that shows that spatial profile of the excitonic fraction can be very different from the profile of the photonic fraction. So I wonder if it would have any effect on this soliton physics.
I would say that these results that you are mentioning will be probably of quantitative nature, right? In the sense that all these approximations, I'm working here in the polariton basis, right? But if you work in this exciton photon basis, what you get is that the dispersions will contribute to these profiles of the solitons, but they will not change the very nature of this potential, right? So your potential will remain short range because these structures, the solitons, are localized, right? So there's no way that even if you go to another basis, so if you go to another sort of approximation, that you change. I don't expect any change, qualitatively speaking, in the dispersion relation. So you will still be able to see this first sound on the soliton gas.
Well, I would cautiously expect that if the density of polaritons changes on a scale of the Healing length, then these are wave vectors of the order of inverse Healing length that play, and probably on this kind of wave vector range, you have a strong dependence of the interaction constant because of the Hopfield coefficient.
I agree.
I don't know.
I agree, but at that scale, so for this kind of these wavelengths, the theory is not expected to be valid anymore because it's very unlikely that you can describe the solitons as pairwise interactions only. So you have to use these 3 body interactions, 4 body interactions, and all these contributions at the small scale will change the whole physics, right? So here it's as I said in the presentation, we are expecting this to work up to the inverse of the wave vectors that are inverse of the density of the soliton gas. Fortunately, it works a little bit further, but it's for reasons that we cannot expect. But in principle, it's only designed, this theory is designed only for the low wavelength limit of the soliton gas regime dynamics.
Okay, thank you. Nikolai had a question.
Hugo, Thank you very much for your interesting talk. I just looking at your slide and question about Vlasov equation. Vlasov usually it's about the Coulomb long range. And what about the long range, short range character of the interaction of your solitons?
I totally agree with you. This is a very nice, this is, from me, it's a problem of nomenclature. So if I go here to this Vlasov equation like this, what I call Vlasov, of course, Vlasov is for long range interactions. It was designed initially for Coulomb. If you want, this should be called a Vlasov-like equation in the sense that these potentials are short-range. But what is important here is that this potential here appears from the fact, so it appears from the Klimovich procedure, right? So you construct this equation from the same Klimovich equation that you work out for plasma physics, but here you neglect by neglecting the collisions. And because of the spirit of the approximations that I use to derive this equation, I call it Vlasov equation, the same procedure that we use for plasma, just because of that. But of course, I agree that you can probably be, because historical reasons, Vlasov was derived for long-range potentials. You have to pay attention here whether or not this is Vlasov equation. Well, let's call it a kinetic equation with zero collisions. Yes, I agree.
Okay, thank you very much. I believe we have two more questions. David, okay, a short one, and then we move on.
Yeah, a very short one. Thanks, Alexei. Thanks, Hugo, for the great talk. So I saw you were skipping through the slide, but you were showing this giant on-Sagar vortices made in some experiment in Australia. So what was the connection you wanted to make with this quickly?
Exactly. So I haven't time to explain, but these experiments in Australia show that you can see what is predicted by this on-Sagar theory in equilibrium of so-called condensation of vortices, right? So if you produce a negative temperature vortices, you can have this separation of vorticities as you have in the first plot, and in the bottom plot, if you have the temperature larger than 0, you have this or disordered gas. But these are what we call, I understand this to be equilibrium or near equilibrium situations. What we wanted to do, what I wanted to see is that whether or not with this kinetic equation, which allows you to go far away from equilibrium, is whether or not you can, from an instability mechanism, go relax in one of these situations. So imagine that you start with a certain random or a very specific situation of vortex configuration, where this vortex configuration is out of equilibrium, and I want to see how it evolves towards, if it's possible to evolve towards one of these equilibria here that is described in these experiments. So this would be a manifestation that the kinetic description is valid, because it allows you to go via relaxation mechanisms towards the equilibrium, right? So an equilibrium is reached after, if you include properly collision operators in the right-hand side of your equation, right? So this is one aspect. The other aspect was really to investigate instability mechanisms in vortex and soliton gases. So if you have streaming of vortexes, for example, if you have one mechanism that is very well known in plasma physics is this two-stream instability that is very responsible for many of astrophysical turbulent situations. If you have two streams of vortex going against each other, for example, would you assist or not to do the equivalent of this two-stream instability, the equivalent of that? And this is something that you can describe with these kinetic equations. Right. So this part, this experimental thing, was just a motivation.
Sorry. No, guys, please. Yeah, we need to move on. I'm sorry.